So today's lecture, we're going to be looking at angular kinetics. So we just finished up angular kinematics, which was the study of movement without respect to force and mass. So what is angular kinetics going to be? Study of movement around a circular path, right? Angular movement with respect to force and mass. So from our linear kinetics, what were the main quantities we were focused on looking at? We looked at momentum and we looked at impulse, and specifically the relationship between impulse and momentum. So we're going to be looking at those quantities today from the perspective of angular kinetics. So when we're looking at angular kinetics, we can ask ourselves all kinds of questions. So why does a discus thrower spin? How does that help improve their performance? How does a long jumper run in the air, right? Or fold forward in the air, right? So if you watch somebody run and jump, they don't just like run and whee, right? Do the Super Mario jump. They're going to be performing some movements in the air that help to stabilize them. And a really big one that we're going to hopefully have a really good demonstration of today is why do figure skaters or divers or gymnasts speed up or slow down, and how do they do this while they're in the middle of a rotation? Okay, so first of all, how can they achieve this? And second of all, why would they want to do that? When we looked at our linear quantities, we said that inertia was quantified by what? So what was the quantification of inertia for linear momentum, or for linear kinetics? Mass. Awesome. So since we had some quantification of inertia for linear, we must also have a quantification for angular kinetics. And now we're not just interested in how heavy something is, how much mass it has. We're actually interested in where is that mass located relative to the axis of rotation. So we call this the moment of inertia. So moment of inertia is getting at this concept that mass can be distributed away from that axis of rotation, and the farther away it is, the harder it's going to be to cause a change in the state of rotary motion. So if you think about swinging a sledgehammer, right? Sledgehammers have most of the mass concentrated at the head of the sledgehammer, and if we go to swing it and we hold it right from the very end of the handle, how easy is it going to be to swing that sledgehammer? Practical example, is it easy? No, right? We're going to choke up on it first, get it moving, and then let your hand slide down once it's already moving. So it's going to be much easier to move when the mass is closer to the axis of rotation. If we think about it, every particle of mass resists being accelerated. It resists having its motion changed. And if we move those objects farther away, they're going to be harder to rotate. Now, we call this moment of inertia, so that's our quantification of inertia, and it's represented by the mass of the object times the radius of gyration squared. So the radius of gyration is, you can sort of think of it as the average location or distribution of mass away from the axis of rotation. Now, to be very clear, it is not just how far. So we say that this is the axis of rotation here, and we have a mass here. It's not just the distance of where the center of that mass is to the object. It is the distribution of mass of all of the parts of that object away from that axis of rotation. So when we're looking at our equation there, I equals mk squared, what can we draw, and what information can we draw from this? What affects our moment of inertia? So mass and radius of gyration, but which one's going to have a stronger effect? Yeah, the radius of gyration is going to have a much stronger effect because our mass is a linear relationship. So 1 unit increase of mass equals a 1 unit increase in moment of inertia. But with radius of gyration, it's an exponential relationship. So the farther away we distribute the mass from the axis, it's going to have an exponential relationship, so the more it's going to affect our moment of inertia. So if we looked at this, taking a relatively light weight and moving it farther away from the axis of rotation is going to have a much larger effect than just holding a heavier weight at the same distance. Again, it's not just the length or the measurement from the axis of rotation. It is dealing with the distribution of mass of the whole object around that axis of rotation. So if we have an object that is free to rotate, so we take, well, we'll flip my thing. It's going to rotate around its center of gravity, and its resistance to rotation will be determined by the moment of inertia, so that resistance to change in angular motion. So its moment of inertia then is related to the distribution of mass around each separate axis. So when we look at measurements in 3 dimensions, I can change where my mass is located, and that can affect my resistance to rotation around 1, 2, or all 3 of my axes. So if I wanted to minimize my axis of rotation, or my radius of gyration around all 3 axes, what would I need to do? Yeah, if I just tucked into a ball and brought everything as close to the middle of my body as I possibly could, it would bring all of my mass as close to my axis of rotation as possible. What would happen if I just raised one arm out to the right and up? Is that going to, which axes will this affect? So let's start with the x-axis. Is this going to affect my radius of gyration for my x-axis? Okay, yeah, it is, right? It's farther away. What about my y-axis? Not particularly, right? Because these are all just still rotating around the same way. What about my z-axis? I see a couple heads nodding. Yeah, that's absolutely going to affect my radius of gyration around my z-axis. So when we change body position, we need to not only look at what limb moved and where, but how does this affect the body's ability to rotate? So particularly if we become a free object, so we're rotating in the air. Now we see this a lot in sports where we have athletes performing rotations. So figure skating is a classic example of this. Ballet is a good example of this, right? Where you'll see them do something like this where they rotate out and then they spin and tuck in. And I can't do that very well because I'll fall, but well, I'm already dizzy. But that's the whole premise, is they're adjusting their radius of gyration to allow them to perform different actions, okay? If we look at the phases of something like that, so we're going to perform that spin, what we notice is I start with my hands kind of stretched out. What happens when I stretch my hands out? Yeah, I'm increasing my radius of gyration. I'm distributing my mass farther away from my axis. What is that going to do for my ability to rotate? Yeah, it's going to be harder for me to rotate. It's going to slow down my rotation. Why might that be advantageous at the beginning of the skill? Control. Yep, so momentum will be conserved, meaning that when I tuck my arms in, whatever momentum I had with my arms out will be conserved, and it's just going to make me go faster, and we'll talk a lot about that coming up. But something else is really important. If I want to produce force, so if I start producing force with my leg to cause this rotation, if my hands are already tucked in, I'm going to start rotating while I'm trying to produce force. Meaning what about my ability to produce force? I'm going to produce less overall force, and I'm going to have less time to produce that force because I'll already be in rotation. So by slowing down my rotation, it gives me more time to produce force, and it gives me more force, right? Because I won't start rotating right away. And when we looked at our equation for linear impulse, what makes up linear impulse? Force and time, right? So the more force I apply for a longer period of time, the more impulse I have. Are we going to expect a different relationship for angular impulse? Probably not, right? So what we've noticed so far is that most of our angular quantities are going to match up pretty well with what we saw in a linear sense. So if I want to increase my force, in this case it'll be torque, but if I want to increase my force and increase my time, I need to first slow down my rotation. Then once I've got the momentum that I want, I can then tuck in and allow myself to spin around that axis. So another example of where we can see this is in something like running, okay? How many people see professional sprinters run like this? Right? I feel like this is not a very commonly observed technique. Why not? Besides the fact that it looks a little goofy. Okay, maybe a lot goofy. Oh, it's definitely not efficient. It's going to take a lot more energy. Also not going to go very fast. You're not taking advantage of all your joints? I'm not taking advantage of all my joints. What specifically about my joints do I want to take advantage of here? Okay, everybody stand up. And without kicking your neighbors, swing your leg this way, and then swing your leg with your knee tucked. Okay, first of all, besides the hamstring stretch, which one was harder? Straight leg. Straight leg's harder. Why is straight leg harder? It's heavier. Is it heavier? Did your leg change weight? It's further away. So what did we do? Yeah, we increase the radius of gyration when our leg is straight. If we increase the radius of gyration, what happens to our moment of inertia? It increases exponentially, right? That's bad. That makes it harder. So it's literally harder, meaning it would take more force for us to accelerate the same mass of our leg just by keeping the leg extended. So by tucking the knee while we're going through our swing phase, right, we can drive our leg up, and it's going to end up going much faster for the same force input. Okay, so if I'm trying to push as hard as I can, drive my leg as fast as I can, I'm literally going to be able to move it faster because there's less resistance to me rotating my leg. We see this also in things like pole vaulting, where we're going to have multiple movements. Okay, so we need to, first of all, get our body upside down. Okay, so if I want to get my body upside down, what axis do I need to change my radius of gyration around? So I want to go this way. I need to reduce my radius of gyration around my y-axis, and we see that. So we're going to tuck into that pike position. So by tucking into a pike, oh God, right, we're decreasing our radius of gyration around the y-axis, making it easier to rotate upside down. Okay, then we look at this position, and now we're going to spin around our z-axis. So to spin around our z-axis, what do we want to do? We want to get everything tucked in nice and close to the pole, right? So imagine I'm upside down. I want to bring everything in and rotate around my z-axis, okay? That's going to allow me to get upside down and turn around so I can push off over top of the bar. So throughout the skill, we need to modify our radius of gyration around multiple axes at the correct time to optimize our performance. Now, we talked about in golf how we get an advantage by having a longer club, right? What does the longer club do for us? So we have our angular velocity omega, okay, and we have our radius. So our tangential velocity is those two multiplied. So we said it's an advantage to increase the tangential velocity at the point of impact. But what we just said is that if our club is extended, it's harder for us to swing the club, right? So what do we want to do in our golf swing? Now again, I'll bring out my big practical stick. Okay, so if this is my golf club, very extended golf club, okay, am I going to swing it like this? It increases my radius of gyration, meaning that it is easier or harder? Harder for me to swing it, okay? So if I tuck my golf club up and I keep it tucked until I'm on the downswing, like partway through the downswing, I'm going to be able to accelerate the club head much faster. All that's important is that at the point of contact, I have my radius maximized. So we don't want to reach that full extension until we're right near that point of contact. If we can do that, it allows us the longest period of time to accelerate the club with as little resistance as possible, right? So we want to minimize that radius of gyration to lower the moment of inertia, meaning that I can get the club going as fast as possible angularly before I increase that radius of gyration. Because as soon as I increase the radius, I move that mass farther away, it's going to slow me down. When we talked about our linear momentum, what was our equation for linear momentum? Mass times velocity. And what is mass? The quantification of inertia. So we can actually think about it as inertia times velocity. So when we look at our angular momentum, which we represent as L, okay, so we have L equals our inertial quantity, I, times our angular velocity, omega. We can break this down and say that I equals mk squared times omega. So now our angular velocity, or angular momentum, is mk squared times omega, or our moment of inertia times the angular velocity. Okay, so it's actually, again, the same principle as we had with our linear measures, where it's just inertia times velocity. The difference now is that we can actually modify two different components of our inertia. So when we talked about our linear momentum, we said that if we have a change in linear momentum, it has to be a change in velocity, because why? We can't change the mass. Unless something falls off of the object mid-flight, we can't change the mass of the object, right? So the only thing that could change in linear momentum is the velocity. But now we're in a situation where we could change the velocity, or we can change the distribution of mass away from the axis of rotation. So we can change that radius of gyration. That means that we can now change both the inertial quantity and the velocity. And that's really important for us, because we have a fun demonstration. So what we're going to do is we're going to make her spin with a large radius of gyration. So lots of weight held out. We're going to go nice and slow. And then as she tucks her arms in, and arms out to slow down, arms in to speed up. Awesome. Okay, so what's happening there? what we're dealing with is the concept of conservation of angular momentum. Okay? So we have L equals IW, or I omega, right? So when we break this down into this formula again, we can see that we can adjust this quantity. So one way we can think about this is I'm going to represent the letters as big or small. So to maintain the same angular momentum, so conservation of angular momentum, because we're not, once she's spinning, we're not applying any additional torque to her to cause her to rotate. Okay? We can have a small moment of inertia and a large angular velocity, or we can have a large moment of inertia and, well, it's like a little smaller, and a small angular velocity. So in order to conserve her angular momentum, as she tucks her hands in and brings the weights closer to reduce the radius of gyration, she has to speed up to compensate. So her angular velocity has to increase in order to balance this equation and conserve angular momentum. So when we think about conservation of momentum, it's just saying that we can't change the momentum of an object without applying a net external torque, right? So if we have some angular motion, we can't make a change to that angular momentum without applying a net external torque. So just like with our linear sense, when we talked about Newton's laws, with linear momentum, we can't change our linear momentum without applying an impulse. Now we have the same situation. We have to have an angular impulse to change her angular momentum. But we can have the same angular momentum with different angular velocities. Now, what would be a good way of stating what angular momentum is? An object in rotation or angular motion has a tendency to stay in angular motion unless acted upon by a net external torque, because we were talking rotation. Think about the skill of long jump. So we have two main techniques for long jump. One technique is that as you're in the air, you kind of start running and windmilling your arms. Okay? The other technique is we run and we jump and then we fold forward into a pike position. So take a couple minutes and discuss with a group why we would do either of those techniques. Why can't I just run and jump and do the Super Mario pose? All right, let's hear some ideas. Okay, so I'm running, I run, and I take off for my high jump. Why can't I Super Mario pose? So what would happen if I didn't do one of those two things? So I run, and I exert a force back into the ground that acts and kind of goes through like this, below my center of gravity. What would happen if I apply a force below my center of gravity? Is this a very good way to land? Probably not optimal, right? And the more force I apply, right, the more I'm going to rotate. So effectively, at takeoff, we give our body some angular momentum. Okay, so now thinking about that, why might I want to either run and windmill or pike? Yeah, I'm basically swinging my body forward to create some angular momentum going this way. So I'm using my muscles to swing the upper body forward so that I can create some momentum that counterbalances my rotation. Because ideally when I land, I either want no backwards rotation or even maybe some forwards rotation. Pretty hard to get forwards rotation if you actually push off hard enough though. But the goal here is to prevent ourselves from falling backwards or laying out on your back and decreasing your jump distance. So because we start off with some backwards angular momentum, right, we need to counteract that with some forwards angular momentum. So I can swing my arms and windmill my legs. I'm not coordinated enough to do that, so I'm not really going to try. Or I can just move forward into that pike position to swing my upper body forward and counterbalance that backwards momentum. What about running? Okay, who here runs like this? Oh, this is always so hard. Ugh. Right? First of all, incredibly difficult, much harder than it looks. So why don't we run with our right arm and right leg at the same time? Yeah, exactly. If I create angular momentum going this way, I'm going to land like this. Then I have to swing back and land like this. So by alternating, having my right leg swing forward, at the same time my left arm swings forward, that creates a counter torque, meaning that I get some angular momentum going this way, some angular momentum going this way, and when we sum those momentums, it results in, hopefully, 0. Now, what would happen if I was just walking, okay? So walking is a good example because we can do it without our arm swing. Okay, I can walk like this, and it might look a bit goofy, but I'm not wobbling around all over the place. Okay? But more commonly, who here has a heavy backpack? Okay, I'll do it a little bit more exaggerated. Awesome, you can have a seat, thank you. Okay, so if we walk normally first, so I'll have a very vigorous gait. Right? So we're nice and vigorous, we're walking with purpose, trying to get somewhere, and then we decide to carry our heavy backpack or heavy briefcase in our hand. What's changing? Swinging a little bit differently, swinging much less or much slower, much smaller magnitude. Why doesn't it have to swing as much to counterbalance my torques? It's so much more mass. So if I swing that mass, if I were to walk with the same amplitude, I'd now be walking like, oh God, like woo, right? I'd be swinging myself. Every time I put my right leg forward, I'd be like whee, flying off to the side. And we don't want to do that, right? So when we're looking at the goal of walking or running, we don't want any net rotation around our z-axis. We want to just be going in a straight line. Anything we do to rotate is going to be inefficient. So it's an accessory movement that we don't want, right? So by modifying the amplitude or how much I swing my arm because of the weight, I can still produce the same counter torque. And we went from having a big, vigorous arm swing to like just a little teeny motion, and that was enough to create the necessary torque to balance out my leg swinging. Just to reiterate, angular kinetics still follow Newton's laws. So when we talked about our object in motion, right? We can talk about it as an object at rest has a tendency to resist a change in angular motion unless acted upon by a net external torque, right? And we use torque because torques are the forces that cause rotations, okay? So if we change our moment of inertia, then we must have a change in angular velocity to compensate and maintain that same momentum, okay? So whether I'm in no motion or uniform angular motion, this principle will apply. So this is Newton's law of inertia, right? So basically it's just stating that if we have an object at rest or in uniform motion, it's going to stay at rest or in uniform motion unless acted upon by a net external torque. The difference here is that we can actually maintain the same momentum while changing our uniform motion, our velocity. Okay, so if we maintain the same angular momentum, but we modify our radius of gyration, we can not violate this concept, but still change our angular velocity. So we're going to take the hurdling examples. We previously talked about this a little bit in terms of our center of gravity, right, and our flight height to maintain an appropriate flight trajectory over the hurdle. Now we're going to talk about it from a little bit more of a holistic view. So we want to talk about all of the movements that are happening and how those movements affect our ability to successfully hurdle. So we're going to look at these series of images, and I've got a bit of a top-down breakdown for you here as well. And I want you to look at those movements that are happening, and within your group discuss why each of these movements needs to happen, what it's doing to modify your radius of gyration, why we need to modify the radius of gyration at that point, and what that means for the overall success of the skill. Let's start off with what is the goal in terms of angular momentum in the skill? Do I want angular momentum? Yeah, I just want to go forwards. I'm not trying to do this. So if I took off and I had my lead leg go over and I take my trailing leg and I swing it across like this, how am I going to land? I'm going to go, and that's not going to be very efficient for my running because now I'm going off the track, right? So let's talk about why we have these movements. So my leg swings, which is going to give me angular momentum in that direction. So what do I need to do to counterbalance that? Yeah, I need to rotate my torso and my arms, okay? So our goal is to look at the sum of angular momentum of all limb segments, because that contributes towards the body's total angular momentum. So if my leg swings and generates angular momentum going this way, my arms have to swing back the opposite direction, and that's going to counterbalance, create a counter torque, counter angular momentum that cancels out to 0. Now, if I just swung my arms, is that going to be very effective? If I'm a hurdler, there's a very good chance that the mass of my legs is much larger than the mass of my arms. So if I swing my one gigantic leg, I know it's not the same. If I swing my one gigantic leg and I have my tiny little arms, it's not going to cancel out. So it's actually going to require some rotation of the torso as well. So if we want to counterbalance, we're going to have a little bit of rotation of the torso added, because the torso has lots of mass. And because it has lots of mass, do I need to rotate it really fast? No, right? It's got lots of mass, so I can rotate it just a little bit, and it's going to create a lot of angular momentum. Okay? So the goal here then is to use the sum of the angular momentum of each limb segment to look at the body's overall total angular momentum. And the goal here being that we take off in a straight line and we land in a straight line, because then we can keep running towards the next hurdle. If we rotate sideways and land, well, first of all, you might fall over, and best case scenario, you're no longer running forwards.